Hello and welcome again to the Path to Plutus channel. The goal of this channel is to help you along your path to becoming a decentralized applications engineer by teaching you a powerful programming language called Haskell and then a subset of Haskell called Plutus, which will allow you to build native smart contracts on the Cardano blockchain, should you so wish. The previous video in the series of videos on learning Haskell walked through lists and working with lists and the different functions that you can execute on lists. It's a very useful video. Lists are the most used data structure within the Haskell functional programming language. So if you haven't checked that out or any of the other videos in the series, do please go and head over to the channel, subscribe to the channel and check out any of the other videos. Do please like and share any of the ones that you enjoy. And there is a channel introduction video which goes through why I'm doing this, why functional programming is important. So they're all worth checking out. And each video is just another step in your path towards Plutus. So we'll kick this video off now. The goal of this video is to go through tuples and the Haskell type system more broadly. So we'll look into how, what makes Haskell a statically typed language and, how it all fits together really. So we'll start with tuples. They have some similarities, very, very vague similarities when it comes to lists. And I'll explain what I mean by that in a bit. But basically, tuples are a way to they're a way to group things together into a single entity. So with a list, you might have an undefined number of unrelated things. So you might have, the numbers 3, 6, 7, 8, 9 in a list, and that list can be as long as you want. There's no restriction on the size of that list. You can add further elements, and that's not a problem at all. Once you define that list is a constant and doesn't change. But in creating that list, you can create a list of any length. Whereas tuples are a bit different. You group related things in a single entity, and it has a fixed size. So tuples really are useful for when you know how many components make up an entity you're trying to represent. And you can represent many different things with tuples. And we'll go through examples on how to create them and what they look like. So what's interesting though about tuples is that by defining one, you're defining a new type. When you create a list, just like the one that you can see on the screen now, when you create a list, you're not creating a new type, you're just using an existing type. Lists are defined as something of is something that has any number of elements of type A. So that means that lists are homogeneous. So everything in the list has to be the same, right? So you use an existing type which can store an unlimited amount of values, again, of type A. But with tuples, you're actually creating a new type. Which is why this lesson has combined tuples and an introduction into, or a bit of a dive into Haskell's type system, because they are interlinked. Because as you're defining a new type by creating a tuple. So, what you can do with tuples is you can combine different components of different types in a single entity. So that's why I was going on a little bit, a few seconds ago about lists having elements of the same type. And the reason I repeated that a couple of times is because that's different to tuples, which can have different components of different types. So tuples don't have to be homogeneous, unlike lists. So that's something that you need to bear in mind when distinguishing between the two. So let's go on to creating a tuple. So I've spoken about it for quite a bit now. So a tuple, you start defining a tuple by typing parentheses. So an open and closing parentheses. If you have programmed previously and you have interacted with languages that allow you to create tuples, this is normally the way that it's done. And in Haskell, we start by defining parentheses, so an opening and closing parentheses. Just like if we began to define a list, we would use open and closing square brackets. So open and closing parentheses just says we want to define a tuple and nothing else. And what you do is in between the parentheses, you specify your components, and they're all just separated by commas, just like in a list. When you're adding elements to the list, you separate them by commas, and you'll get a list. Except I haven't started the Haskell compiler, but you'll get a list back from that. So 593, you'll get a list back. Okay, so let's go back to defining a tuple. So that's open and closing parentheses, and what I'm going to do is I'm going to include two components of two different types. So as you can probably see from the background, we're going to talk about staking in this lesson, Cardano staking. But before we get to that, I'm going to show you how to define a tuple, and that tuple is going to be staking themed. So let's suppose we wanted to represent a way of tracking how many blocks have been produced by a staking pool. If you have some understanding of staking, you'll know what that means. If not, what I'll do is I will switch over to this presentation just to basically run through it so that everybody's on the same page. So in Cardano, the smallest unit of time is a slot. So if you think of this ruler as representing slots, each slot is the smallest unit of time. In a slot, in one of these slots is where a block is produced. A brand new block is created, which has transactions in it. Okay, so a slot, as specified on this slide, lasts 20 seconds. One slot takes place every 20 seconds. Okay, so that's the first thing you need to understand. And slots are grouped into what are called epochs, or I've heard them being referred to as epics. I'm not sure really what the correct pronunciation is, but I thought it was epoch, and there was a great video done by Addertainment on YouTube, which explains this in great detail, and it was referred to as epics there, which is something I didn't expect. So I don't know what the debate is. I googled it. Some people say it's epoch. Some people say it's epics. So whatever your preference is, you go for that. And I'm sure if you have a strong opinion about which way it's supposed to be pronounced, then please do let me know in the comments. I'd love to settle the debate. But anyway, so the slots, each of these slots that last 20 seconds, they're grouped into an epoch. I'm going to go for epoch. It might annoy some people, or epic, but and there's 21,600 of them in an epoch, right? So that means they last 5 days, and epochs are special because So at the start of every epoch, what are known as slot leaders are chosen. So for each and every one of these slots, as we go along here, a slot leader is selected, and the job of a slot leader is to be online when it's their turn to be a slot leader for that particular slot. So when the time comes along and it comes to their slot, they need to be online to produce new blocks which contain transactions, and that process is done at the start of every epoch. So this is a very important concept to understand as a blockchain developer on the Cardano blockchain. But going back to our command prompt, say we wanted to represent a way of tracking how many slot leaders. So by the way, a slot leader is the same as is basically the same as a stake pool. That's how the staking is structured in Cardano. So what you have is you have stake pools, and you delegate your stake to your stake pools of choice. Your funds never leave your wallet, and this is very, very important, just in case you're researching staking further and some scam artist tells you that you have to send all your ADA to their stake pool directly. That's not the case. You get, as part of your wallet and as part of the Shelley release, you will get your own spending key to spend your funds, but you'll also get your own staking key to delegate your stake. So please do not send your stake to any nefarious stake pools. There will be scams in any cryptocurrency project. Just don't fall prey to those scams. So you are fully aware, and they have spoken about this quite a lot on the Cardano effect. Massive fan of the Cardano effect. So they've spoken about that a lot. So please keep your eyes and ears out for any scams and try and avoid as many of them as possible. But the basic thing to understand is your funds never need to leave your wallet. So you can do things like cold staking from a Ledger Nano S, which is great. So that aside, now that we hopefully have a basic understanding of staking, we want to represent a way of which stake pools have and how many blocks they've produced. So that's the number of slots that they've been slot leader for, and it's proportional. The way it's structured is it's proportional to the amount of stake a stake pool has. But what's clever about the Cardano protocol is that the maximum amount of stake that a stake pool can possess is equal to 1 divided by K, where K is the maximum number of, or the desired number of stake pools. So at the moment they're aiming for 100. So they want to have at least 100 stake pools producing blocks. They want to be, that's quite decentralized. So you can have a lot of stake. And this incentivizes people to, if a stake pool has already hit the maximum number of stake that can be delegated to it, it incentivizes people to go to other stake pools where not as much stake has been delegated over, so that you can get the maximum amount of rewards possible. But that's just a bit of an aside. Enough. I've digressed quite a bit here. So we're going to represent in a tuple the name of a stake pool and how many blocks it's produced as slot leaders, how many slots it has been part of. Okay, so without further ado, we're gonna so to represent the stake pool name, I'm going to use a string, which, remember, the type under the hood is a list of chars, list of characters. So I'm going to use that as my first component in the tuple, and then as the second component, I'm going to use an integer, which is going to represent the number of blocks produced. So Let's say Path2 Plutus channel had a stake pool. So Path2 Plutus stake pool. Okay, and let's say produce 45 blocks. Okay, so the fact that an error hasn't been returned means it's been successful. So that's the first tuple created with you guys. So this tuple represents, like I've said a few times, the fact that the Path2 Plutus stake pool has produced 45 blocks as slot leader. And again, going back to my comparison with lists versus tuples, lists have to be homogeneous. Every element has to be the same type, but with tuples, they do not have to be homogeneous. So you can have different types for every component, as you have here. You have a string or a list of chars, and you have an integer here. And if you hit the up arrow to display the previously typed command, and then prepended it with :t, what :t does, if you prepend anything with :t, you'll get the type, the underlying Haskell type, for an entity. So here, right, it says, okay, so we have the tuple with Path2 Plutus stake pool, the number 45, and this double colons, basically you read it as has the type of. So this tuple on the left has the type of blah on the right. Don't worry about this for the time being, but basically you can see we have a list of chars, and you have the b, which represents the fact that we have an integer as the second component. But don't get too caught up in this syntax. I'll talk about it in another lesson. It requires its own lesson, really. But basically, you can see that we have the underlying type, and we've created a new type. This is a brand new type in Haskell's eyes. So what you can do is you can say, I want to. I'll have a function which takes a tuple that it has as its first component a list of chars and the second a number, and you can supply any combination of strings and numbers. It doesn't have to be any specific one. Okay, so that was a quite an in-depth slash brief medium introduction into staking and tuples. So now, as we've sort of discussed previously, things can be compared. Lists can be compared, numbers can be compared, and so can tuples. Tuples can be compared if their components can be compared. Okay, so if we bring up the previous example, if I then copied this tuple, let's just copy that, and we tried to compare it and we wanted to ask Haskell, is this equal to this other tuple that we have? It will come back and it will say true. And so a string can be compared with a string, so that's fine. It's something that can be compared, and a number can be compared. Now, what I'm saying might sound really strange. You know, you might be thinking, well, yeah, surely you can compare a string, surely you can compare a number. And when it comes to types and creating our own types, which programming languages allow you to do, languages, as you can see, allow you to give you a basic set of types, often referred to as primitive types, and then they'll give you the tools to build your own type to represent data, and representing data is a really important function to have in a language. So we need to be able to understand that, really. So when it comes to creating our own types going forward in future lessons, in Haskell, they don't automatically become things that can be compared against each other. If Haskell has never seen something before, it won't know how to compare it. You know, if a new product gets invented on the market, you know, in a new category on its own, you know, something that's never ever been seen, you know, before, it's hard to compare it against something else. It's the same sort of concept in the programming world. If you create a new type, Haskell doesn't really know what to do with it, so you have to sort of give it pointers. But I'm jumping ahead a few lessons now, but you just need to bear in mind that not everything can be compared, not everything can be ordered, not everything can be displayed. If we create a new type, we have to give that type the ability to do those things. So that's just worth bearing in mind. There are some useful functions that you can call on tuples. So just like with lists, lists have their own operations that can be performed on them, and tuples are no different. So one of the first things that I want to, first functions I want to go through is the function that's called FST. Okay, so this function here takes as one argument a tuple. So this is a singular tuple on the right that will get passed into this function first. And as you can see, it takes and extracts the first component of the tuple out and returns it for you. So in this case, the first component of my tuple was the string path to Plutus stake pool. So it's gone and found that and extracted it out for me. So, you know, imagine if I had a list of, stake pools, that might be useful. You know, say for example, we had the list that had as its first tuple that, and then we defined a second tuple, and this time we're tracking the IOHK staking pool, and it's produced 856 blocks, or yeah, it was slot leaders for 856 times. Then we would end up with a list of tuples, and you can do that because so lists can have elements of the same type, and these are all the same type. If I tried to add another tuple and added in an extra param, maybe another number, I'll get an error because the first two types, whilst they match in the, you know, in a tuple way, the third tuple doesn't match at all. So Haskell throws an error and says, you know what, the list isn't homogeneous, the types aren't the same, so I can't do that. But anyway, so you could imagine first being used to iterate through this list, extract every tuple, and then extract the first component of every tuple. That might be because you might want to produce a separate list which just has a list of stake pools. You might not want to care. Say for example, this data was provided to you externally. You might not care about how many blocks have been produced as slot leader. You just might care about the list of stake pool names that have been that are on the blockchain at the moment. So that's a reason why you might want to use the FST function. But there's something that's interesting to note about the FST function. So FST only works on pairs. Now a pair is a tuple, and a pair is a tuple that has two components. So 1, 2. A triple is a tuple with 3 components, etc., etc., etc. So a first can only work on a pair. If you try and use it on anything else, it won't work. So that's worth bearing in mind. And you can get the second component of a tuple by using the function snd, so second, and that will return the second component. And again, you could loop through the list that I previously defined, and you could just end up with a list of blocks produced, and then you could even say, for example, you ended up with a list that had the number of the blocks produced by each stake pool, you could then run that list through sum, and you could get the current block height. So, you know, those are things that you could do with that. You've just got to know how to solve those problems and how to represent data. So the simplest way of representing data, when you know how many components there are going to be part of that data, is to use a tuple. You can do some, a number of interesting other things. You can actually create tuples from two lists. So, say for example, we had independently, we had the list stake pool names. So let me define a stake pool name list. So stake pool names, and we'll set that equal to a new list. So this one stake pool is called the path to Plutus stake pool. The next one is IOHK's stake pool, and the third one is Emergo's stake pool. So that has stake pool names, and I can pool names. So that prints that one out. So let's define blocks produced. Blocks produced. That'll be equal to 55, 9, whatever, just a random number. Okay, now I have purposely produced a list that only has 2 elements, whereas stake pool name has 3 elements in it. So it's got the names of 3 stake pools, and then we have the a separate list which has the number of blocks produced by each, but I've missed off Emergo's. And I'll show you why that's important now, because what you can do is you can use the function zip, and you can zip 2 lists together, and what it does is it will go through every list. It will go through the list one by one, and it will take the first element of this one, and then it will take the first element of the other list, and it will create a tuple. So if you don't believe me, I will show you. Zip stake pool names, and then it has a second parameter which is the other list, so blocks produced. Okay, so there you go. It's created a new list for me, every element of the list is a tuple, and it has 2 components. One is a string and one is an integer. Stake pool name, blocks produced. Stake pool names, block produced. But notice the Emergo element from the stake pool names is not present. So zip is smart enough, and there are a lot of handy functions like this in Haskell which work to the shortest list. So in this case, the shortest list was the blocks produced. So it will only ever produce a new list that has the same number of elements as the smallest list. So it produced a list of 2 elements because the shortest list provided to zip had a size of 2. One of the use cases really for zipping is it gives you the ability to traverse 2 lists at once. So you could traverse the stake pool names list and then the blocks produced list independently. But if you wanted to traverse them both at the same time, you could zip them together like this, and then produce a new list of tuples, and then you can iterate through each element and do any data manipulation or data crunching that you need to do, and it's the same as going through the list independently. So that's quite a cool use case for zipping lists. If you want more examples on how to zip lists, do check out the Learn You for Haskell Great Good book. All the content in this course is based on that book. As I've mentioned in the previous videos, I really enjoy it, and I get a lot of inspiration from the book for these tutorials. And also, by the way, if you have any videos or books that you'd like to recommend that can influence the course, or any Cardano content that you'd like to see, please do feel free to drop a comment. The Twitter username for this channel is @Plutus2. I will link it in the description, so please do feel free to interact with me as much as possible. Anyway, back to the video. So let's look into Haskell's type system more closely. So, as previously mentioned, Haskell has a static type system. So, the type of every expression is known as at compile time. So, when we were previously defining a list, this is an expression. The expression results in the definition of a new list. And if this was in a file and Haskell was compiling it, i.e. translating it from code into something the machine can understand, it would know what the type is of this new list. It's a list, and it's a list of integers more specifically, because remember, lists have to be homogeneous. So this leads to errors being caught sooner rather than later. Errors are caught at compile time rather than at runtime. There are still going to be runtime errors, but the amount of errors are reduced. And this is quite similar to languages like Java or C, C++. But unlike those languages, Haskell has type inference. So notice when I whilst I'm defining this new list, I don't have to specify that it's a list. In Java, the equivalent Java declaration might be something like you have I don't know, a list of integer, and that is called new list, and then you have to create a new object, and so on and so forth. You have to explicitly give the type of that list, whereas Haskell has type inference, so it's able to determine on its own what the type is of every expression, and then once it's determined the type, it is able to catch errors much more quickly than languages like JavaScript, which are interpreted on the fly as code is being executed. So understanding the Haskell type system is really important, and something that we need to do. I previously showed you the use of :t. So :t allows you to determine the type of something. So if I give it a list of, so maybe Ouroboros releases, we have Ouroboros BFT, we have Classic. So this is a list, and we can get the type of this list. So using :t by prepending it. So this list on the left has the type of. Remember, the double colon gives you has the type of. It's a list of where every element is a list of characters, i.e. a string, and that it can only be that type and nothing else. So that's quite useful. You can find the types of other things. So if we do :t for the letter C, that's C has a type of char, so the type of Hoskinson. So this is a list of chars, as I've previously shown already. So I've shown you the type of pairs, and we can look at what the type of this expression is. 6 is equal to 6. So 6 is equal to 6 is an expression which has a type of bool. The outcome of running 6 is equal to 6 is either a true or false value, and in this case it's a true value. Now, functions have their own type signatures, and we can give you a quick overview of this. So in a previous lesson, I think it was the first lesson, when we built our first function, we built one of the functions that I built was the acronym buster function. So the acronym buster function was defined as follows. So we defined the label acronym buster, and so it took as an input an acronym, And then we use the equals to define function body. So we also used conditional. We said if the acronym is equal to POS, so then we're going to return that it is that acronym is proof of stake. Otherwise, we're going to return, I have never seen that before. Okay, so that defines the function, and then we can call it with an acronym, and we can supply it that proof of stake acronym, and it tells me that's proof of stake. Now, because of type inference, Haskell is automatically able to infer the type of this function, and we can use :t on this function, and let's see what we get by doing that. Okay, so acronym buster is a function that has the type of list of char, which it has the type of something that takes a list of chars and returns a list of chars. And I know it returns it because I know this syntax, this right arrow, denotes the fact that it returns something. And there can be more than one arrow, but the last thing in the list is always something that's returned. So if the last thing in the list of if the last thing in a sequence of arrows is what is returned from the function, then everything before that is its inputs, right? So again, it takes a list of chars and returns a list of chars. So takes a string, returns a string. The same function signature can be written as this. So we take a string and we return a string, right? So far, that's much more readable. So we take first input is a string and our output is a string, but we can make that even more readable. So one of the things that you can do is you can rename types in Haskell, and you can do that by using the type keyword. So string is the same as a list of chars. The way it's done is by using type synonyms in Haskell, and to create a type synonym you just do type and then string or your new name and what you want it to be equal to. So this is how the type synonym is defined. So every time Haskell encounters a string, it knows that it's actually a list of chars. And you can do that in any way, in any other way that you like. So rather than a string referencing a list of chars, I can say, oh, actually, I want an acronym to be a list of chars. So I'm going to define that, and then I also want a new type called definition to be a list of char as well. So what that means is that I can completely rewrite the acronym buster definition. Okay, so acronym buster, the acronym buster type signature definition is what I mean. So acronym buster function has the type of, because remember the double colons can be read as has type of, and I can say it takes an input of acronym and returns a definition. Now, for both acronym and for definition, they are both strings. They both map to char lists under the hood, except what I've done by defining a type synonym, and it's pretty much like doing a type def in C if you've come across that before. But what I've done by defining a type synonym is I have made the function type signature significantly more readable now. So I improved it by having this type signature string to string. Okay, so that was an improvement, but I can make it even more readable now by having this type signature definition. Right, so we can easily see, so somebody new to this function who hasn't ever come across this function before can read this type signature now and can say, okay, right, we have an acronym buster function and it takes an acronym and returns a definition. Right, and that's quite nice, and it's really, really concise. I haven't had to look into the definition of this function to ascertain what it exactly does. I can see from the type signature what it should do, and if you define your Haskell functions well enough with type signatures, because obviously Haskell does have the type inference, so it can produce a type signature on its own. But if you give it a type signature for every function, then you end up with functions that are significantly more readable and just easier for new programmers to interface with. And if you're going to become a smart contract developer, the more readable your code is, the better for everybody. The easier it is also to spot mistakes. It also enforces the inputs and the outputs that are possible with the function. So that's been a really sort of it's been a bit of a dive into types. You're starting with looking into tuples, and then the Haskell type system itself. We're going to continue the work on the type system as we go through more lessons in the Haskell series on the Path to Plutus channel. So I do appreciate you taking the time to watch this video again. I hope you have enjoyed it. Please do like it if you have, share it, and also subscribe to the channel if you haven't. Thank you very much.